Okay, so let us continue. So, before the break we learnt about the 5 different names that we have for magnetic materials as per physics. Then we learnt that ferromagnetic materials have neighboring spins parallel to each other, and in the case of ferrimagnetic materials the neighboring spins are antiparallel to each other, but they are of different magnitudes. Okay, so, this is how the ferrimagnets look like, and in antiferromagnetic materials the neighboring spins are antiparallel. And so on. Okay. And in the case of paramagnetic materials the neighboring spins are random and they are also fluctuating as a function of time. Yes, so diamagnetic materials are totally different category. So, they have closed shells. So, they do not have uncompensated spins. So, they have closed shell. And we also learnt that paramagnetic materials will be weakly attracted and diamagnets will be weakly repelled, and ferro and ferrimagnetic materials will be strongly attracted, and antiferromagnetic materials also will be weakly attracted. Okay, so, these are common man's definition: weakly attracted, weakly repelled. We cannot do, I mean, in physics we have to measure things, right. So, we cannot define something based on weak repulsion, weak attraction and so on. So, we have to measure something, we have to measure some properties, then classify the materials based on measurements. So, that is physics. Okay. So, we use some advanced equipment to measure the magnetic properties of material. So, one such equipment that we use commonly for measuring the magnetic property is called vibrating sample magnetometer, or in short is called VSM. So, VSM is used for measuring the magnetic properties of materials, and this technique works based on Faraday's law of induction. So, you would have learnt in your college days that if there is a time varying magnetic flux, then if you have a coil in the vicinity of a time varying magnetic flux, then you can observe a voltage. Okay. So, Faraday's law states that the voltage picked up by a sensing coil is proportional to the time varying magnetic flux. Okay. So, if there is a time varying magnetic flux, we can sense a voltage, and this is the principle that we use for vibrating sample magnetometer. Okay. So, this is roughly the configuration. So, you can see we place the sample here. So, this is the sample we want to measure, and this sample is placed between 2 electromagnets. So, with these electromagnets we can produce a magnetic field. Magnetic field can go from right to left or left to right. We can change the direction, and by changing the current that we send to the electromagnet, we can also change the magnetic field. So, we can change the magnitude of the electromagnetic field, or we can change the direction of the magnetic field. So, that is the purpose we have electromagnet. Okay. Then these two pickup coils are the one which are going to pick up the voltage. Okay. So, what happens is that during the measurement the sample will be vibrated. Okay. So, if the sample has a magnetic property, there will be a magnetic flux. So, that magnetic flux will be changing as a function of time, and these pickup coils will give you certain voltage. So, based on this voltage we can measure the sample's property. Okay. So, for this purpose we do something called calibration first. Okay. So, let me erase and let us say you have a known sample, let us say commonly nickel is used as a calibration sample. Let us say this nickel sample has a 500 micro EMU. So, I am using the CGS unit. Okay, this known sample has 500 micro EMU. So, I place this in the VSM and I look at the voltage produced by the pickup coil. Let us say pickup coil gives me 100 millivolt. Okay. So, now I know that so based on this, right. So, I know that 1 millivolt correspond to 5 micro EMU. Okay. So, by measuring the properties of a known sample, you can calibrate how much voltage correspond to how many micro EMU. Okay. Now, let us say I place some unknown sample. And this unknown sample gives me 12 millivolt, for example. Then I know that the magnetic moment of this sample is 12 times 5, 60 micro EMU. Okay, so, this is how we measure the magnetic moment of the sample. Okay, so, EMU is a magnetic moment. So, if you want to measure magnetization, we have to divide the EMU by either volume or weight, mass of the material. Okay. So, in VSM we usually measure the magnetic moments in micro EMU or milli EMU, nano EMU kind of thing. Okay, so, let us go into the details of VSM. Okay, so, here I also say that typically in most VSMs you can change the magnetic field from minus 20 kiloohrsted to plus 20 kiloohrsted. Okay, so, this is a video of the VSM. So, you vibrate the sample, you vibrate the sample. If the sample has certain magnetic moment, it produces a magnetic flux, and the magnetic flux changes as a function of time. So, if you look at the pickup coil, when the pickup coil, the magnetic flux sensed by the pickup coil will change as a function of time. So, based on that we will get some voltage, and based on that voltage we can calculate the magnetic moment. Okay, so, I briefly explain how we can use VSM to measure magnetic property. So, moving forward we will try to answer these three questions. So, how do different materials respond to a magnetic field? So, we learnt that there are 5 types of magnetic materials, how they respond to a magnetic field, and we have been learning about ferromagnetic materials, and these are the most useful materials. So, what are the different types of ferromagnetic materials, and we will also learn why certain materials are permanent magnets, why certain materials are not permanent magnets. So, these are some questions we will answer moving forward. Okay, so, let us go to the first question first. How do different materials respond to a magnetic field? Okay, so, to measure the magnetic properties, what we do? We plot MH curves. What it means is that we go from 0 magnetic field to certain positive field, then go back to a negative field, then come back to 0. Okay. So, H will go from 0 to some positive field, then positive field to 0, then 0 to some negative field, then negative field to 0. Okay. So, we go through this process. So, this is how we usually measure the magnetic properties. So, this is the field sweep. Then while sweeping the field, for every field we will measure the magnetic property M, magnetization. Okay, so, if you do that for paramagnetic materials, let us say you go from 0 to certain magnetic field, the magnetization will steadily increase. So, it will go in a straight line. So, it will go in a straight line, and let us say you stop at this field. Now, you go back to 0, then it will come back in the same line. Okay. So, going up and coming back for paramagnetic material is in the same path. So, similarly, if you go to the negative direction, it will go like this, then you go back, it will go like this. Okay. So, paramagnetic materials will have a positive slope, and this slope is what is called susceptibility. Okay. So, earlier I showed you something. Okay. So, I said this axis is called 1 over chi. I did not tell you what that is. Okay. So, now I tell you that chi is the slope of this curve. So, the slope of MH loop of paramagnetic material or diamagnetic material gives you M over H, that is called susceptibility. Okay. So, now let us say I place diamagnetic material. So, I place copper in between the poles of a VSM and measure the MH curve of a diamagnetic material, then it will go like this. So, it will go in a negative direction. Then if I go back to 0, it will go back along the same line, then again it will go like this. So, go up, then again come back. Okay. So, diamagnetic materials have a negative slope. So, we can say they have a negative susceptibility. So, if I give you a sample, so I give you a piece of material and I ask you to find out whether this is a paramagnetic or diamagnetic. What you can do, you take the sample to VSM and look whether the M goes up or down, or I mean whether it is positive slope or negative slope. So, based on these two slopes, you can find out whether the material is paramagnetic or diamagnetic. Okay. So, typically this slope of paramagnetic materials slope is much larger than diamagnetic slope. Okay. So, even though I tried to make this slope larger and this slope smaller, but this slope is usually much smaller than this. Okay. So, the susceptibility of diamagnetic materials is much smaller than paramagnetic materials. Okay, quite often, if I just ask you to differentiate between paramagnetic material versus diamagnetic material, this measurement is enough. Okay, you do at room temperature, that is enough. But suppose I ask you to find out whether the material is paramagnetic or diamagnetic or antiferromagnetic. Okay. So, now I am confusing you with 3 options. Okay. So, I give you a sample and ask you to find out whether it is para, dia or antiferromagnetic, then this measurement alone is not enough. Okay. So, you have to measure the susceptibility at different temperatures. Okay, so you let us say so I measure the slope at temperature T1, temperature T2, temperature T3 and so on. So, I measure the MH curve at different temperatures and plot the susceptibility, I mean take the slope and plot the susceptibility as a function of temperature. Then I will get different properties. Okay. For example, in the case of paramagnetic materials, the susceptibility will vary as 1 over T, which means if temperature is increasing, the susceptibility will decrease. Okay. So, this, if you see this behavior, then that is a sign of paramagnetic material, and if the susceptibility is independent of temperature, then that is diamagnetic. Okay. And if the susceptibility goes up and comes down as a function of temperature, and if you see a peak, then that is a sign of antiferromagnetic material. Okay. So, you notice that here it is 1 over T behavior. So, this is like diamagnetic. Okay. This is the region where there is no ordering, which means the antiferromagnetic material go from this state to this state. So, from antiferromagnetic it becomes paramagnetic above certain temperature, and this temperature is called Néel temperature. So, in the case of ferromagnetic material, ferromagnetic materials exhibit Curie temperature. So, below Curie temperature they are ferromagnetic, and above Curie temperature they are paramagnetic. So, in a similar sense, antiferromagnetic materials have a Néel temperature. So, below this temperature they are antiferromagnetic, and above this temperature they are paramagnetic. Okay. So, here this point is called Néel temperature, and above Néel temperature, here the temperature is increasing from left to right. So, high temperature, low temperature. So, when at high temperature, above Néel temperature, you see they are like paramagnetic, but below Néel temperature they have a different behavior of susceptibility. Okay. So, if you see a peak, then you can say this material is antiferromagnetic. Okay. So, if I ask you to find out whether material is paramagnetic or diamagnetic or antiferromagnetic, what you have to do is you have to measure the susceptibility at different temperature and plot the susceptibility as a function of temperature. Okay. So, when you plot, if you get this, then you can say it is antiferromagnetic. Okay. So, that is how we can differentiate between paramagnetic, diamagnetic and antiferromagnetic. Okay. So, they are very simple. The magnetization will either increase as a function of H or decrease as a function of H and so on. Okay, now let us move on to the other two types. Okay, before that let us do some questions. Okay, most of you are right. I don't know why I get answer like this. Faraday's law is the correct answer. Next one. Okay, the answer is in the board. I don't know why I still get wrong answer. Answer is here. Paramagnetic materials have a positive slope. So whoever is giving this answer, please wake up. Okay, most of you are right. So antiferromagnetic materials exhibit a peak in susceptibility. Okay, so I told you that the measurement of paramagnetic or diamagnetic materials, the behavior is very simple. Either you have a increasing slope or decreasing slope. Okay, but when you try to measure the MH curves of ferromagnetic materials or ferrimagnetic materials, the MH curves are not simple like this. Okay, so they exhibit a complex feature, which is what we call hysteresis loop. Okay. So let us say I put a piece of material, ferromagnetic material, in between the poles of a VSM, and I measure the ferromagnetic material. So when I increase the magnetic field from 0 to H, I won't have a straight line like this. Okay. Rather, what I will observe is something like this. Okay, it's not a straight line. You see, it goes up like this. Now I reach a certain point where the magnetization is saturated. It doesn't increase anymore. Okay, now I go back to the negative field. Then the MH is not coming back in the same path. Okay. In the case of para or dia, the going up and coming down, the paths are the same, but here the paths are different. Okay. So I go up this way, then when I return, I go back in another path. Okay. So I go like this. Okay. So here again it has saturated. Okay, now I try to go to the positive value. So I won't go along this path. I'll go in another path. Okay, so you see this path is again different from this path. Okay, So, finally, somewhere here I will meet. Okay. So, here again I will saturate, the magnetization will get saturated. So, instead of a straight line that we got in the case of para or diamagnetic material, we have a loop. Okay. So, this loop is called the hysteresis loop. So, from the hysteresis loop we can get many different parameters. So, these parameters define what type of ferromagnetic material you have. Okay. So, one parameter is called the saturation magnetization. I mean, this is the magnetization that we got after we saturate the sample. What happens is that at this field, all the spins or all the magnetic moments are parallel to your applied field. Let us say this is your applied field, all the spins are completely parallel. Okay. So, this is when you will get the highest value of magnetization, and this is what we call saturation magnetization or MS. Okay. So, this point is called saturation magnetization, and when you come back to zero field, so at this point maybe many magnetic moments are still in the direction where you applied the magnetic field, but some of them have reversed. Okay. So, some magnetization have reversed to the opposite direction. So, as a result you may have a slightly lower value at this point. Okay. So, this is called remnant magnetization. Okay. So, this is called saturation magnetization. Saturation magnetization. MR is called remnant magnetization. So, you can say that you have applied some field, removed some field, but still many of the magnetic moments are still remaining in the same direction. So, you can say remnant is somewhat like the remaining magnetization in the same direction. Okay. So, that is called MR. Okay, now I go in this direction. So, I am applying a field in the opposite direction now. Initially I was applying field in certain direction, now I am applying field in the opposite direction. So, that will make some of these magnetic moments to switch. So, at some point you will have roughly half in the same direction and half in the other direction. Okay. So, at this point the magnetization becomes 0. Okay. So, this field, I mean I have applied certain field, and at this field the magnetization is 0, and that field is called coercivity. So, at certain negative field the magnetization becomes 0, and that field is what we call coercivity. And if I increase the magnitude of this negative field, again now all the magnetization will be in the direction of my magnetic field. Okay, so, it will saturate in the other direction. Okay, so, this is also MS. This is also MS, this is coercivity, and this is also coercivity, and this is remnants, and this is also remnants. Okay. Okay, so, this kind of property is obtained in ferromagnetic materials as well as ferrimagnetic materials. Okay. So, when we learned about magnetic recording, it is important that you know what I am talking about. So, I will be talking about MS, MR, coercivity and so on. So, you should remember all these things. So, what I usually ask is, I ask my students to close the eyes, then trace the hysteresis loop visually. I mean, just close your eyes, trace the hysteresis loop, and assign these points on the hysteresis loop. Okay, so do a mental exercise now. 30 seconds. Okay, close your eyes and do. Okay, so there will be test. I want all of you to give the correct answer to represent MS, MR, and so on. Okay, so we just learned how different magnetic materials respond to a magnetic field. So paramagnetic, diamagnetic, and antiferromagnetic materials will show a linear behavior, and ferro and ferrimagnetic materials will show some kind of non-linear behavior. Okay, so now we focus on the ferromagnetic materials, because the magnetic materials that we use for magnetic recording are basically ferromagnetic materials. So let's focus on them. So the question is, are there different types of ferromagnetic materials? So I told you that in ferromagnetic materials the neighboring spins are parallel. Okay, then how do we differentiate? How can we have different types of ferromagnetic materials? That's what we are going to discuss. Okay, so before that, let's do some question. So what is this point? Okay, so one of you didn't do the exercise correctly. Okay, most of you are right. A is called saturation magnetization. Next one, what is point B? Okay, let's consider this as error. Most of you are right. Okay, next question. Okay, point D. Okay, more wrong answers. Okay. The correct answer is remnant magnetization. Okay, so now let's move on to learn the different types of ferromagnetic materials. So I told you that in all ferromagnetic materials, the neighboring spins are parallel like this. Okay, but how do we differentiate between two types of ferromagnetic materials and what are they? Okay, so we can classify ferromagnetic materials into two types based on their hysteresis loop behavior, coercivity, and remnant magnetization. So they are called hard and soft magnetic materials. Okay. So the definition of hard and soft is relative. Okay, there is no absolute number that below which you will say this is soft, above which you will say it is hard. It's a relative term, but in general the definition of hard and soft is based on the coercivity and remnant magnetization and MS saturation magnetization. So usually the hard magnetic materials are used as permanent magnets. So if you have a permanent magnet, the poles are always north and south, you will have difficulty in changing the polarity. Okay. So permanent magnets can retain the polarity. For example, if you make north in certain direction, which refers to this one, then the north pole will always remain in this direction. Okay. So to change the north pole to south pole, you need to apply very large magnetic field. Okay. On the other hand, let's say you take a pin, safety pin, let's say you magnetize, so it will have certain polarity, and you can easily change the polarity by again bringing it closer to a magnet. So you can easily change polarity. Then such magnets are called soft magnetic materials, and usually soft magnetic materials are used in electromagnets, transformers, and so on. Okay. So the differences are that the coercivity is high for permanent and the hard magnetic material, and you can see the difference in the hysteresis loop, right? The coercivity is low for soft magnetic material. So this is one main difference. Usually the hard magnetic materials will have very high coercivity, soft magnetic materials will have low coercivity. And usually the soft magnetic materials will have high saturation magnetization, and hard magnetic materials will have low or moderate saturation magnetization. But if you look at the MR, the remnant magnetization is usually high for permanent magnets, hard magnets. The remnant magnetization is very low. You see, this is the saturation magnetization, and the remnant magnetization is very low for soft magnetic material. So this is how we differentiate between hard and soft magnetic material. As I mentioned before, there is no clear rule to define which is hard, which is soft. It's all relative. Okay. So to give you some idea of the kind of field I am talking about, so I say coercivity is high. How high is high? How low is low? And so to give you some idea, I am giving you some idea of field here and some idea of the material property here. Okay, for example, if you take the Earth's magnetic field is like 0.00005 Tesla. If you take a neodymium iron boron bar magnet, the bar magnet can produce like 0.1 Tesla. And if you go to some hospitals where they do MRI and so on, there they have very strong magnets like 5 Tesla magnets and so on. So you can see the different kind of field that you can see in the Earth. Okay. And now I show the material property. For example, neodymium iron boron is a hard magnetic material. So, it has a coercivity of 1.5 Tesla. That means, if you want to change the polarity of this neodymium ion boron magnet, you need something like this 5 Tesla magnet, okay, to change the polarity. On the other hand, if you take iron, a piece of iron or permalloy, which is an alloy of iron and nickel, they have very small coercivity, which means even with a neodymium ion boron bar magnet, you can change the polarity. Okay. So, here hard or soft basically means how easy or difficult is to change the polarity of the magnet. So, I have certain magnet, this magnet has north pole here, south pole here. So, if I want to change the north pole to south pole to north pole, I need to apply certain magnetic field. So, if this applied field is very large, then we call it hard magnet, and if the applied field is very low, then we call it soft magnet. So, this is the difference between hard and soft magnetic material. So, when we talk about recording applications, okay, now I ask you a question, which material we want for recording application? Huh? Soft? So, how many say soft? Huh? Both, okay, yeah. Okay, for storing information, so for storing information we need a hard magnetic material, but for writing information we will use a electromagnet to write information. So, there we use a soft magnetic material. Okay, then we will go into the details later, but this is to give you some idea. Okay, you would have come across many different magnetic storage materials like tape. How many of you have seen magnetic tapes, the cassettes? Okay, so few of you have seen. Then have you seen the old credit cards with a black stripe at the back? Okay, then okay, so these are also magnetic recording. So, old credit cards and tapes are also magnetic recording. So, in these materials the coercivity is only around like 700 to 900 Oersted, okay, which means if you apply a field more than 700 Oersted, the information in your tape or credit card will get erased. Okay. So, I just showed you before that a neodymium ion boron magnet can produce 0.1 Tesla. So, 0.1 Tesla is 1000 Oersted. Okay, so, if I put my credit card, old credit card, and a neodymium ion boron magnet in my pocket, then I will lose all the information. This magnet can erase the information in the tape or credit card. Okay. But if you move on to the hard disk drives, I mean hard disk drives also long back they had coercivities of these values, but these days the coercivity of the hard disk drives are like 6000 Oersted or 7000 Oersted, much larger than the magnetic field that can be generated by permanent magnet. So, usually the permanent magnets won't erase the information of hard disk drive. Okay. So, this way I am giving you some idea. Okay. Even I mean this is also considered hard long back. These materials are also considered hard materials in the past. These are also hard magnetic materials. Okay. So, the definition is relative. Okay. So, compared to iron, for example, which has a coercivity of 10 Oersted this is still large, right? So we call them hard magnetic materials. So magnetic materials can be dangerous. So quite often in foreign countries, when there is a magnetic field inside some room, they put sticker. Okay, they put magnetic field inside so that you take care. Okay, so this one incident that happened in Bombay, that they have a MRI machine which generates 5 Tesla, and this guy goes with a cylinder, gas cylinder. So the gas cylinder gets pulled and he gets stuck and dies. Okay, so magnetic field can be dangerous also. Okay, so we learnt about two different types of material: soft magnetic materials and hard magnetic materials. So now the next question is, why some materials are hard, why some materials are soft? Okay, what makes some materials to be hard, what makes some material to be soft? Okay, so the answer to this question is magnetic anisotropy. So before we move on, are there any questions so far? Okay, if not, let's move on. Okay, magnetic anisotropy is the one that makes material hard or soft. Okay, so before we learn about what is magnetic anisotropy, let me just start with isotropy. Isotropy means you measure some property. The measured property is independent of the direction in which you measure the property. For example, let's say I take a copper wire. I measure the resistivity of the copper wire in this direction or in this direction. The resistivity I measure should be independent of the direction. Okay, so whether I measure along this direction or the other direction, the resistivity of copper is one number and it is not going to change. So the property I measured is independent of the direction in which I measure. So I call it isotropic. Okay, so when some property is independent of direction, we call isotropic. And the word anisotropy is the opposite of isotropy. Okay, suppose I measure the property of something and it is different in two directions, then we call it anisotropic. Okay, so magnetic anisotropy means the magnetic property that you measure will be different in different directions. So if you get different properties in different directions of measurement, then you call it magnetic anisotropy. Okay, for example, if I take a sheet of paper, okay, imagine this is a magnetic material. Okay, so I measure the magnetic property along this direction and along the direction towards you, and if the properties are different in the two different directions, then we call it in plane magnetic anisotropy. So within this plane there are two directions. In one direction we have one set of property, in another direction we have another set of property, then we call in plane magnetic anisotropy. Okay, so here I have defined two words, right, hard and easy. Okay, easy direction means you can change the magnetization. You can increase the magnetization with very small magnetic field. For example, I apply very small magnetic field, only this much. So within this the magnetization goes up like this quickly. Okay, so this is one possibility. Another possibility is I apply some magnetic field, the magnetization is only here, I apply more magnetic field, it is like this, then slowly it is getting saturated. So, we call this as hard, okay, which means we need more magnetic field to bring the magnetization higher, and this is what we call easy. Okay. So, in easy direction we can reach saturation with very small magnetic field, and in hard direction we need more magnetic field to reach the saturation. So, if a material has one easy direction and one hard direction, then we call that material to be magnetically anisotropic. Okay. So, you see that in different direction we have different property. So, we call this as a magnetic anisotropy. So, if within the plane of a material one direction is easy, another direction is hard, then we call it in plane magnetic anisotropy. Okay. And let us say we take the film again. So, we have a magnetic thin film. So, in this thin film, let us say the perpendicular direction is easy. I mean, you can easily bring the magnetization up, but you need a very large magnetic field to bring the magnetization to the in plane direction. Then we call it perpendicular magnetic anisotropy. Okay. So, this gives you some idea of the anisotropy, but let us discuss more in detail. Are there any questions so far? Okay, so let me use some analogy for anisotropy. So, I told you that isotropy means it is direction independent, anisotropy means direction dependent. Let us say you have a flat open ground. Okay, so, it is a very large ground and it is flat, and say you drive a car from here to here or here to here, you will find no difference, because it is a flat ground and you assume that the friction, everything is the same, and it is a leveled ground. So, there is no up or down. So, in that case, whether you drive the car from left to right or bottom to top, the driving is going to be the same. Okay. You press the accelerator to say 1500 RPM, then your speed is going to be the same in this direction or this direction. Okay. So, it is direction independent, and we call this as isotropic. Now, imagine another road. Let us say it looks like this. Okay. This road has this shape. Now, driving in which direction is easy, along this direction or this direction? Okay. So, this direction is going to be easy, right. So, you have one easy direction and you have a hard direction. So, we can say driving along something like this is anisotropic. Okay. So, you have an easy direction and you have a hard direction. So, that is one thing. So, here you press accelerator 1500 RPM. When you come here, the speed is already 80 km per hour, and in this direction you press the accelerator 1500, you cannot even climb up. Okay. You need maybe more revolutions to climb up. Okay. So, that sets the difference between easy and hard direction. That is one difference. Can you tell me any other difference between the easy and hard directions here? Okay. Okay. So, what I want to say here is, okay, in the isotropic case, right, I move the car from here, apply brake, stop, it will stop here. I drive up, stop here, it will stop wherever I stop. Okay. So, similarly, in the anisotropy case, if I drive along the easy direction, let us say I stop the car here, no brake, but the car will still remain here. Okay. But in the hard direction, when I try to move the car up, I stop the accelerator, no brake, then the car will come back to the ground state. Okay. So in the hard direction, there is no equilibrium. Equilibrium is somewhere else. So if you leave the car here, car won't stay there, it will come back to the ground state. Okay. So similar behavior you can also see in the hysteresis loop. Okay. So these are two hysteresis loops in the easy direction and hard direction. So you can see two differences. First difference is, like with very small magnetic field, I can saturate quickly. So that shows the easy nature. Here I need more magnetic field to saturate the sample. That's one difference. And okay, I saturate and I remove the magnetic field. That means at this point, right? So most of the magnetization is remaining in the same direction. So that's like the car. So I bring the car somewhere here, stop, then the car is still there. Okay. So that is equivalent to having a large remanence. Okay. On the other hand, in the hard axis, let us say I apply certain magnetic field, I saturate. If I remove the magnetic field, then it is going to the remanent state, 0 state. Okay. So these are the two differences between the hysteresis loop and in the easy and hard direction. Okay. Let us say my easy direction is like this. I apply a magnetic field in this direction. So the magnetization will rotate, and if I remove the magnetic field, then the magnetization will go back to the easy direction. So the magnetization will always remain in the easy direction. So if you take the magnetization away from the easy direction towards hard direction, if you remove the magnetic field, it will go back to the easy direction. That is why you have these two types of hysteresis loops. Okay, so this magnetic anisotropy can come from various origins. So based on the origin of the anisotropy, we have various terms to explain this anisotropy. So the first term, first kind of anisotropy is called magnetocrystalline anisotropy. So as the name implies, this anisotropy comes from the crystallographic properties of the sample. Okay. Then second is called shape anisotropy and interface anisotropy and so on. So we will learn a few types of anisotropy in the next few slides. Before that, any questions? So is the concept of anisotropy clear? So yesterday we learned that there are various types of crystallographic structures. One structure is called hexagonal closed pack structure, and the cobalt belongs to the hexagonal closed pack structure. So if you take a unit cell of cobalt, it will look something like this. So you will have 7 cobalt atoms here, and there are 3 cobalt atoms here, and again 7 cobalt atoms here, and we learnt that this axis is called A, this is B, and this is C. Okay, so in the case of cobalt, the C axis is the easy direction. That means the magnetization, if you do not do anything at remanence, the magnetization of all these cobalt atoms will point in the easy direction. So they will either point up parallel to this, or point down anti-parallel to this. Okay, so that is the easy direction, and any direction other than the C axis is a hard direction. So the plane, these planes are hard directions. So you cannot make the magnetization to be parallel to the planes. Okay, so the easy direction is always pointing up. Magnetization either pointing up or pointing down. So if I take a piece of cobalt material and I try to magnetize the sample along this 0, 0, 0, 1 direction, which is along the C axis, then I will notice that the magnetization quickly goes up, and very soon the magnetization is saturated. Okay. So, this is the easy direction. So, 0, 0, 0, 1 is the easy direction, because I can bring all the I mean ideally when you do not do anything, all the spins are already in this direction. So, you do not need much magnetic field. So, some grains in the cobalt material that you have studied maybe in some other direction, that is why you need some magnetic field in the case of real experiments. So, you will notice that quickly with very small magnetic field you can bring all the magnetization to one particular direction. So, this is the easy direction MH curve. On the other hand, let us say I apply a magnetic field along 1 bar 0, which is the hard direction. I need a very large magnetic field to bring the magnetization towards this direction. Okay. So, you see I keep increasing the magnetic field, slowly the magnetization increases, and finally it reaches close to saturation. Okay. So, this is the difference between easy direction and a hard direction. Okay. So, this is an illustration of what happens when you apply magnetic field in the easy and hard direction. So, here we are applying a magnetic field in the easy direction. Okay, I will play again. So, all the magnetization is pointing towards your magnetic field. Wait, let us go here. So, in the easy direction, all the magnetization is pointing towards your magnetic field, and once you remove the magnetic field, they are still pointing in the same direction. So, this is the direction in which you applied magnetic field, and they are pointing in the same direction. Okay. So, they have a large remanence. On the other hand, when you try to apply magnetic field in the hard direction, easy direction is here in the perpendicular, I mean the vertical direction. However, you are applying a field in the horizontal direction. So, horizontal direction is hard, vertical is easy. So, when you apply field in the hard direction, the magnetization slowly rotates towards your magnetic field. So, you see the magnetization slowly rotates and aligns towards the magnetic field, but once you reduce the magnetic field, it goes back to the ground state. Okay. So, this is the hard direction, easy direction is in the vertical direction. Okay. So, this is what happens in the case of cobalt, and cobalt is called, I mean in cobalt we have magnetocrystalline anisotropy. Okay, then there is another type of anisotropy called shape anisotropy. So, as the name implies, this anisotropy comes from the shape of the material. So, how many of you have seen magnets which look like this? Okay. So, this is called the horseshoe magnet, and here these magnets exhibit certain hard magnetic property because of the shape. Okay. So, what we have done is that let us say there is a north pole, south pole, then you look at the spacing between the two, the distance between the two poles is very large. Okay. So, this is one example of magnet where we use shape anisotropy to make a permanent magnet. Okay. So, the rule of thumb in the shape anisotropy is that a configuration in which the north and south poles are far away from each other, that is the easy direction. Okay. For example, if you take a cylinder like this, so in this direction, let us say I magnetize the material along this direction, let us say I make this north, this south. So, you can see the spacing between north and south is very large. Okay. However, if I try to make the if I try to magnetize this along this direction, so I will have north pole here, south pole here, north and south are closer. So, this is not possible. Okay, this will be the hard direction, this will be the easy direction. Okay, so that's what I have tried to show here. So when you have an ellipse, for example, you try to magnetize along this direction. So north will be here, south is here, so they are far away from each other, so this is easy. But if you try to magnetize along this direction, north is here, south is here, they are closer to each other, so this is hard. Okay, so usually the shape anisotropy comes into picture in the absence of a strong magnetocrystalline anisotropy. So when the magnetocrystalline anisotropy is weak, then the shape of the magnetic material will determine the direction of magnetization. So if you look at this horseshoe, because they have made a very long cylinder, north and south pole are far away, so this is the easy direction. So they can magnetize like this, then they will bend it to this shape. Okay, so this is an example of shape anisotropy. Okay, so now I have a sheet of paper. Can you tell me which is the hard direction? Yeah, so in the up or down direction. So if I try to magnetize along this direction, the north and south poles will be closer. So this is the hard direction. Then here, which is the hard and easy direction?
Shorter one will be hard.
Yeah, so this is the hard direction, this is the easy direction. So that is the rule of thumb in the case of shape anisotropy. Then there is also another type of anisotropy called interface anisotropy. Quantum mechanically we don't explain, we explain based on the demagnetization terms. Yes. In some other slides I had the formula, but now I don't have.
So it is almost like a thumb rule. That the
Yeah, thumb rule, yes.
Direction
Yes.
Be easy.
Yes. Okay, so the third anisotropy that I want to introduce to you is interface anisotropy. Here, this anisotropy comes when you bring certain magnetic materials like cobalt with some non-magnetic material or antiferromagnetic material and so on. For example, I bring this cobalt in proximity to platinum, or the cobalt in proximity to some antiferromagnetic material like iridium manganese. So I will have some kind of anisotropy. So this comes from the interface between the two layers. So here you have cobalt interfaced with platinum, here you have cobalt interfaced with iridium manganese. So there is some anisotropy coming because of such interfaces, and we call them as the interface anisotropy. For example, suppose you make a multi-layer system of cobalt, platinum and so on. So you make thin layers of suppose you make multi-layers of cobalt, platinum, where cobalt is very thin, 0.5 nanometer, platinum is 1 nanometer and so on. So you stack many layers of cobalt, platinum, something like that. So then we call it cobalt, platinum or cobalt, palladium multi-layers. So in this case, we can introduce a perpendicular anisotropy. Normally, when you have a cobalt layer, the magnetization will tend to lie in the plane. But if you make multi-layers like this, you can make the magnetization to point in the perpendicular direction. Okay. So this is one example of interface anisotropy. And another example is like you interface ferromagnetic materials with antiferromagnetic materials. So in this case, you can see that the hysteresis loop has shifted. Normally the hysteresis loop is symmetric. So if you look at this hysteresis loop, is almost symmetric with respect to this 0 field. However, in this case you see that the hysteresis loop is fully shifted. So, the center is away from the 0 axis. In fact, both reversal happens in one side, right, and this kind of behavior is called exchange bias. So, here again this anisotropy is coming from the interface between ferromagnetic and antiferromagnetic material. Okay. So, this is another kind of anisotropy. Okay. So, these are some examples of anisotropy, and this anisotropy is responsible for the soft and hard magnetic properties. Okay. So, let us do some questions. Okay, so this question I always end up having two different answers. So, who is right, the majority or minority? Minority. Okay. So, when we talk about coercivity, we are talking about magnetization becoming 0, which means half the magnetization are pointing up, half the magnetization are pointing down. Okay. So, it is the field required to reverse half of the magnetic moments. Okay. Next question. No. Okay, the hard magnetic property is not defined by the magnetization. Okay, so it is by the ability to demagnetize. So what it means is, let's say I have a hard magnet with a north pole here, south pole here. So I cannot change the north pole to south pole to north pole easily. I need a very large magnetic field to change the polarity. So the correct answer is this. Okay. Who is right? Majority or minority? Minority. Okay. Let's say you have a piece of sample. Let's call one of them easy and another as a hard direction. Okay, so I measure the hysteresis loop along the easy and hard direction. So in the easy direction, I'll quickly reach saturation, then I'll get some hysteresis like this. Okay. In the hard direction, I'll need a very large magnetic field to saturate. Then when I go back, I may go somewhere along this direction. I mean, it will still go like this. Okay, so if I apply sufficiently large magnetic field, even in the hard direction, I can reach the saturation magnetization. Okay, so saturation magnetization cannot be different. So under very large magnetic field, I can force all the magnetization to be along the hard direction. So the first, this one is wrong, because you thought that the saturation magnetization will also be different in different direction. You choose all of the above, but this is wrong. Okay. Saturation magnetization will be the same in easy and hard direction. Only the field you require to reach this stage will be different. So in the case of easy direction, with this field, you have already reached the saturation magnetization. With hard, you need more field. That's all. I think I am wrong. I clicked the wrong answer. Okay, next question. Here I chose the wrong answer, but 2 is the correct answer. Okay. So even this question you have difficulty. I mean, this is one of the simplest question. So I told you that in the case of shape anisotropy, the one where the north and south poles will be far away is the easy direction. So it should be along A. Okay. So direction A is the easy direction. Okay, so now the question is like let's say you take a piece of iron, you take a piece of iron or you take a piece of neodymium iron boron, you apply a very large magnetic field. So let's say you get north pole here, south pole here, north pole here, south pole here. Okay. So after you remove your magnetic field, the north and south pole of this will be remaining for a very long time. Okay, but in the case of iron, maybe the north south pole will be kept for some time, but after a few hours you may lose the north and south polarity. Okay. So the main difference between a neodymium iron boron and iron is the anisotropy. Okay. So anisotropy, magnetic anisotropy is the one that makes certain materials hard and certain materials soft. If the anisotropy is larger, we will have permanent magnets or hard magnetic materials, and if the anisotropy is small, then we will have soft magnets. Okay, they cannot retain their polarity. So bar magnets are made using hard magnetic materials which can retain the north and south polarity for very long time. So during your school days, you would have learnt that if you heat your magnet, what happens? If you heat your magnet, what happens? What happens? Ferromagnet to paramagnet. No, but you are not heating to that temperature. You are heating to a temperature below Curie temperature. What happens? No, I am not talking about you. Have you learned phase transition in your school? No, right? I am talking what you learnt in school. So in your school, you would have learned that if you heat your magnet, you lose the magnet, right? But we learned that when we heat our magnet, even if we reach Curie temperature, we come back to room temperature, the ferromagnetic property is still there. Okay. So when we say what we lose by losing magnet, is basically the north and south poles that we set, they get lost. Okay. There will be no north or south pole, but this material is still ferromagnetic. So what is the difference between before heating and after heating? So before you heat a material, before you heat a bar magnet, so what happens before heating and after heating is shown by this picture. For example, when you take a permanent magnet, right? Usually, what you do, you take a piece of, you make a cake like neodymium iron boron. You apply a very large magnetic field, and with a very large magnetic field, you force all the magnetization to be along certain direction. Then when you remove the magnetic field, your permanent magnet has all the magnetic moments pointing in one direction. So, you may call this as a north pole, you can call this as south pole. Okay. So, this is how you make a permanent magnet. But let us say you heat your magnet at certain temperature, what happens is that the magnetization are not now pointing in the same direction, but they are in random direction. Okay. This will be the case. Let us say you make a fresh piece of neodymium iron boron. Okay. So, you mix neodymium iron boron powders, let us say you make, then you press them into this shape, for example. Then also you have a piece of neodymium iron boron. Okay. So, when you make a fresh piece of material like that, so in that material also you will see that the magnetization are in random direction. Okay. So, this random direction is different from paramagnetism. Okay. So, we learned in paramagnetism that the neighboring spins are random, right. But here it is not that kind of random. Okay. So, you will have small regions. So, let me draw. So, you have one region, another region, and so on. So, if I zoom this region, maybe magnetization is pointing like this. So, all the neighboring spins are still parallel. And if I go to another region, here maybe the spins are like this. Okay. So, it is still ferromagnetic. So, within each region the ferromagnetic properties maintain, which means the neighboring spins are parallel. But as a system, the ferromagnetic material has divided into many small regions where the magnetization are in different direction. So, in this region the magnetization is pointing up, in this region magnetization is pointing at certain angle, and so on. Okay. So, these regions that a magnetic material form is called magnetic domains. Okay. So, if you take a fresh piece of magnetic material, let us say you melt iron. Okay. So, you take a piece of iron, melt and press it to some shape. So, now you have piece of magnetic material. So, within that magnetic material you will have domains, magnetic domains, which means you will have regions. Within small region the magnetic moments will be parallel, but there will be many such regions where the magnetization is in random direction. Okay. So, that property is called magnetic domain. So, in any material, in many materials, whenever you form a fresh piece of magnetic materials, there are domains and they are in random direction. So, if you remember the hysteresis loop I draw, so I started from here, right. So, magnetization is 0, but we know that in ferromagnetic material all the spins are parallel to each other, magnetization cannot be 0, right. So, why magnetization is 0? Because of the domains. So, when you make a fresh piece of samples, there are regions where the magnetization is pointing in different direction. So, because of this randomness, any fresh piece of sample will have 0 magnetization, but remember within this the neighboring spins are all parallel. Okay. So, ferromagnetic properties maintained because the neighboring spins are parallel, but the system breaks into many regions and the magnetization of those regions are pointing in different direction. As a result, net you will have 0 magnetization. Okay. So, that brings us to this topic of magnetic domains. And so, I draw magnetic domains, right. So, here I have one domain, here I have another domain, and the region that separates two domains is called domain wall. Okay. So, domain wall is the boundary between two neighboring domains and we call this as a domain wall. Okay. So, we will learn a bit more about this in the next few minutes. let's say I have two magnets. So I try to bring them closer to each other. What will happen? What will happen? So both magnets have north pole up, south pole down. I try to bring them together. What will happen? They will repel, or if I still force them closer, I let my fingers a bit loose, then what will happen? Repulsive force, okay. But I still bring them closer, what will happen? What is that? Okay, so what happens? I think someone answered. They will flip, okay. So the north pole of one of them will be up, and this magnet will flip, right? Then you will have south up. Okay, so if they flip, then it will become attractive force. Okay, they will come and stick together. Okay, so remember this one. Now let us say I am building some ferromagnetic material. I am depositing a film, or I am making powder of a ferromagnetic material. So you know that ferromagnetic material has spins parallel to each other. Okay, so there are many spins parallel to each other. Okay, so you can imagine this as a big magnet with the north pole, south pole, right? So if I keep building this, so if I go in all direction, that is equivalent to having two magnets with north pole parallel to each other. Okay. So if I keep building many more spins like this, then that's like this, right? This is a state of high energy. This is a state of low energy, right? So when the two north poles are parallel to each other, you need to spend large energy to bring them parallel to each other. On the other hand, if they flip, then you don't need to put any effort. Okay, so this is state of high energy, this is state of low energy. So when you build a ferromagnetic system, all the neighboring spins are parallel. So when there are more spins, it is like this system. Okay, the energy of the system is going to be high. On the other hand, let us say in some regions the spin has flipped. Okay. Now this is a state of low energy, right? Okay, so now you can call this as one domain, this as another domain, and this as a domain wall. Okay, so here I just used some energy, right? High energy, low energy. So we call this as a magnetostatic energy. So this is high magnetostatic energy, this is low magnetostatic energy. So when we are demagnetizing energy, so we can call magnetostatic energy or demagnetizing energy. So when we prepare any new material, the spins, if all spins are parallel, then the systems will be at a very high state of magnetostatic energy. So they have to minimize by forming domains. Okay. So this is one reason why the domains are formed. Okay. So, in this video you see that we are forming a magnetic material, many spins are parallel to each other, then magnetostatic energy gets larger. But if the system breaks into many domains, the magnetostatic energy becomes minimum. Okay. So, this is the reason why systems tend to form domain. So, if you can minimize the magnetostatic energy, I mean if all spins are parallel to each other, then the magnetostatic energy is large, but if you break into many domains, then you can minimize the magnetostatic energy. So, that is the reason why domains are formed and domain walls are formed between the two domains. Okay. So, these are some examples of magnetic domains. So, you can have one region where all the spins are pointing up, another region where all the spins are pointing down, and in between there is a transition between this domain to this domain, and we call this as a domain wall. Okay. But a domain need not form all the time. Okay. So, there are only certain circumstances so the domain formation depends on the total energy of the system. So, you know that in physics the systems tend to minimize the total energy, not just one energy. Okay. So, the ideal, I mean the ultimate objective of domain formation depends on whether the total energy of the system is minimized or not. Okay. So, I just described one energy. So, one energy is a magnetostatic energy or demagnetizing energy. So, this is the one that increases when we put more spins parallel to each other. Okay. But there are also other energies we need to consider. For example, now let us say we formed domains and there is a domain wall, right. So, this domain wall also needs some energy. So, when you form a domain wall, there are two energies associated with it. So, one energy is anisotropy energy, another energy associated with the domain wall is the exchange energy. Okay. So, there are two energies associated with the domain wall formation. So, let us go back to this picture for example. Let us say this is a sample with a perpendicular magnetic anisotropy, which means the easy axis in the perpendicular direction. Okay. So, these spins are parallel to the easy axis. So, they are at low energy. These spins are also parallel to the easy axis. So, they are at low energy. But if you look at the spins here in the domain wall, so some spins are away from the easy direction. Okay. So, you see these spins are away from the easy direction. So, there is some anisotropy energy. Okay. So, we have to spend some energy to keep the magnetization away from the easy direction. So, there is a anisotropy energy. Secondly, we learned, so when we learnt about Heisenberg exchange interaction, we learned that the spins S1 and S2 has to be parallel, right. So, in ferromagnetic material the two spins have to be parallel, then the Heisenberg exchange energy is low. But if you look at the domain wall, you see the neighboring spins are not parallel, they slowly move from perpendicular direction to the other direction. So the neighboring spins are not parallel. So they make, so if one region is like this, other region is like this, the intermediate region, the neighboring spins make some angle. Okay, they are not parallel to each other. So since the spins are not parallel to each other, there is also an increase in exchange energy. Okay. So when you form domain, you minimize the magnetostatic energy. So domain formation minimizes the magnetostatic energy, but domain formation increases the domain wall energy. Okay. So ultimately, whether a system forms domain or not depend on the total energy. Whether this energy is bigger or this energy is bigger. So depending on the competition between the two energies, the system may or may not form domain walls. Okay, so that's shown in this picture. So here, here I plot the energy associated with the demagnetizing energy or magnetostatic energy is plotted here. Magnetostatic energy goes as a function of volume. Okay, so is L cube. So if L is the length associated with a certain domain, then L cube, I mean the demagnetizing energy goes as a function of L cube. However, the domain wall energy is proportional to L square. Okay. So when the size associated with a certain magnetic particle is very large, so you see that the domain wall energy, I mean the demag energy is much more compared to the domain wall energy. Okay. So what it means is that if size exceeds certain length, critical length, so above this size, it is better to minimize, form domains. So if you form domains, you can minimize this energy drastically. So it's okay to spend some energy to form domain wall, but the total energy will be reduced. So above certain critical size, domains will be formed. But if you go below certain critical size, now the demag energy is lower. Demag energy is lower, domain wall energy is larger. Okay. So below certain size, if you form domains, you are spending more energy. The system will be at a high energy. So it is not worth to form domains. So the system won't form domains. Okay. So this will look very complicated. So let me use some picture to explain what's happening. So in this case, we have a sample where we make islands of magnetic material. So you can imagine a small cylinder. So you have certain diameter and a certain height. And in this case, the diameter of the cylinder is shown like 5 micrometer, 500 nanometer, 200 nanometer, 50 nanometer, and so on. The height is the same. So in all the 4 cases, the height is the same, but diameter is different, which means the volume is different. Okay. So you learned that When the volume is very large, then the magnetostatic energy is going to be large. Okay, so we just noticed that when the volume is very large, magnetostatic energy is going to be large. So in that case, it is better to form domains. So the system forms many domains. To those of you who don't understand what's happening here, we are using magnetic force microscopy, MFM. So magnetic force microscopy basically gives rise to two colors, for example, orange or brown. Depending on the magnetic nature of the sample. So in this case, this sample is a perpendicular magnetic anisotropy. So we can imagine that orange means north poles are pointing up, brown means south poles are pointing up. Okay, so it's something like this. So you can imagine this is orange and this is brown. Okay, so you are looking at two different domains. So here, for example, you have orange or yellow, whatsoever. Yellow means this magnetization is pointing up, brown means magnetization is pointing down. Okay, so in the case of 5 micrometer, you have many such yellow and brown region. Okay, so you may not be able to see all of them, but there are many tiny stripes of yellow and brown region. That means there are many domains within this 5 micrometer. Okay, so domain has formed here. So as per our prediction, when the critical size is large, then the system will be in multi-domain. So you can see many domains here, and you move towards smaller size, 500 nanometer. There are one or two domains. So you have one domain, another domain. Okay. So what you see here is each cylinder. So there is one cylinder here. You are viewing from the top, cylinder, and so on. Here the cylinder sizes are bigger. So this is one cylinder, this is another cylinder, and so on. Okay, so here you have many domains, and here you have one or two domains. And when you reduce the diameter, so when you reduce the diameter to 200 nanometer, sometimes you see one domain, sometimes you see two domains. But when you go to smaller size, 50 nanometer, so each cylinder shows only one pattern. Either they are yellow or they are brown. Okay, which means they are in single domain. There is only one domain. So this explains what we learned before. So above certain critical dimension, here in this case 50 nanometer. So above 15 nanometer, you see multi domains. So it may be one domain or two domain. I mean two domain or three domain or many more domains as you go towards larger diameter. But below the critical diameter, in this case slightly above 15 nanometer, here you will have only one domain. Okay. So that's what is shown in this picture. MD means multi-domain, SD means single domain. So below certain critical size, you will have single domain. Above certain critical size, you will have multi-domain. Okay, so with these questions, we will stop and go for lunch. Let's do a few questions. What happened? Only 9 of you. Is it lunch time? Okay, also many wrong answers. So I told you that the domain formation depends on the total energy of the system. The answer is in the board, but you are all hungry. So it is about the decrease in the overall energy of the system. Pardon? Copy. Try again. नहीं आ रहा है. QR code. Okay. Okay, scan again. Still not.
We are able to log in.
Okay, but the questions are not appearing. Okay. Okay, let me try again. About now? Okay. Okay, formation of domain walls reduces the magnetostatic energy, so this is wrong. But domain walls also increase the exchange coupling energy and is due to magnetostatic interaction. So 1 and 3 should be correct answers. 3 also should be correct. Okay. Next one. Okay, this question tests you how attentive you are. Okay, although I didn't talk about super paramagnetic. My slide shows something like super paramagnetic. So, if you paid attention to the slide, you would have chosen all of the above. Yeah, most of you have paid attention. Very good. The correct answer is all of the above. Okay, so we have some portion left. Maybe after Professor Naresh lecture, I'll continue, and today we will finish this. Okay, we break for lunch now. See you.